Hello and welcome to the video covering our 2023 Capstone project, a Mars facility. Our first task with this project was to do our research. We needed to develop an idea of what our limitations for the project may be. Sending anything to space is a challenge, so we found out what currently operational rocket has the highest payload capacity. This was the Falcon Heavy, which can theoretically carry 26,000 kilograms to Mars, and has these internal dimensions. Mars is also extremely cold, and since it's missing a magnetic field, ionizing radiation is a major problem. We researched materials that would mitigate these issues and tabulated them here. 2. Design alternatives and evaluation. As a group we looked at different construction method ideas. Built there, expandable, or 3D printed. Our concept scoring matrix indicated we should go with expandable. The next step was to look into the types of expandable alternatives. Inflatable, partially inflatable, and foldable. Our concept scoring matrix indicated we should go with partially inflatable. 3. Preliminary sketches and initial CAD. Here we have the concept sketch for the undeployed view. Then we have the deployed view. After this, there's the top view. Next we started on SolidWorks to CAD these sketches. Four. Design changes. Notice in these top images how the corner pieces have a larger width than the rectangles. This is not favorable, as we want the corner pieces to lay flat on top of the rectangles and not stick off. If they stick off, then the panels can't be folded up. To correct this, the team increased the number of corner panels to 3 and the number of rectangular panels to 5. In this image, you can see that we changed the design for the 66 hinges that allow for the deployment and folding of the panels. First it was a butt hinge, but the team decided against this and went with internal hinges. These were then scaled up, and their material was changed to 4,340 steel. 5. Addition of components. Here we have the back side of the airlock door. Currently we see it in the locked position. With the push of a lever, the door becomes unlocked as seen in this image. 2 doors were added to the model, so that the facility could be modular. Next we have a sketch of what we wanted for the anchoring mechanism. We wanted a drill that could lower into the Martian regolith and secure the center of the facility. Here are some CAD pictures and videos of this design. 6. Prototyping. For the prototyping process, we 3D printed 120 scale models of our design, and attached motors to see how the panels could be moved and folded. 7. Iterations and design changes. After prototyping we realized our initial design may not work. We wanted to place servo motors between each panel and fold them that way. However, after calculating the torque required, we realized this would not be feasible. We decided to take a new approach. Instead of motors between panels, we would add winches with cables and pull the panels down and out. To do this we would need 10 winches with 10 cables, and we would need attachments to secure the cables too. The attachments would be designed to be removable, so that a cap could be screwed in their place. Prototyping also helped us find the optimal location for the hole slots that the cables would run through, as seen in this image. Additionally, we needed to come up with a plan for the inflatable material and how it would secure to the habitat. As you can see from this graphic, we added slots along the edge, so that the fabric skin could be tucked into it and fastened. We also added a plate on top of the core of the habitat, so that the fabric could be tucked under it and fastened with 4 bolts. For the winches we also needed an area to rest them on, so we added this rack assembly. 8. Theoretical design versus built prototype. There are 2 major differences between the built prototype and our theoretical design: scale and materials used. We obviously could not build a 1-story facility in downtown Montreal on an $800 budget, so we opted to scale the prototype down to 1/10 the actual size. Additionally, it would be expensive, costly, and unnecessary to make all the components out of their actual materials. We decided to make the following changes. Since we couldn't run some tests on our built prototype, due to these changes, we ran small batch sample tests on some actual theoretical design parts. This will be covered later in testing. 9. Manufacturing and assembly. Since we were using plywood for the floors instead of aluminum, we had to purchase the right amount and cut it to size. Here we used an optimization software to plan out every cut from a 4-foot by 8-foot sheet of 1/2-inch birch. After cutting the sheet into sections, we then needed a wood CNC router to cut the sections to these shapes. Here are the results, and then all of them together. Next we needed to 3D print the core. This failed more than twice, wasting maybe 2 kilograms of plow filament. Here are the results. After this we needed to add butt hinges to the faces of the panels, to allow for folding. The next step was to 3D print other components such as the rack assembly, fabric attachment, and auger housing. We laser cut a piece of clear acrylic to place on top as well. This would allow us to see the motors inside. We made this detachable, if ever we needed to fix the motors or access them. Here are some pictures of the motor assembly, and wiring. We ran out of space to store the microcontroller, motor drivers, batteries, and Wi-Fi modules, so we ran wiring through the bottom to the outside and stored everything there. 10. Validation and testing. Our first test was on the skin of the facility. But before that we ran some simulations on ANSYS to see how temperature resistant our composite material was. After this we sketched some plans for a testing device we could use for a 6x6x6.7 sample of the material. Then we went to SolidWorks and made a CAD of this testing unit. The bottom was to be filled with dry ice to simulate the cold Martian temperatures. Then a probe would be placed to measure the temperature of this ice. The material would be placed on top, and above this would be an isolated air pocket that was in contact with the face of the material. This air pocket would contain another probe. Around this apparatus, we placed a bucket and some insulative spray foam, to allow as little heat escape as possible. Data was then collected via an Arduino. Inflation and pressurization. We also wanted to demonstrate inflation, and see how long it would take. The team designed these attachments in SolidWorks for a nozzle, and connected them to the holes of the doors. Inflation took around 20 to 30 minutes with our low-powered pump. Deployment. With the motors in place and wiring done, the team needed to ensure that the panels would deploy. Individually, each one could easily be lowered, but due to pulley slippage, inconsistent cable lengths and other issues, auto-deployment of all panels was more of a challenge. What the team ended up doing was running a series of tests and timing how long it would take for each panel to hit the ground. Adjustments to the microcontroller's code were made based on these time trials. Hinge stress test. A crucial part in the deployment of this facility is the integrity of the 66 hinges that allow for folding and deployment. After modifying the SOS 208 internal hinge to be 3 times larger, and changing the link thickness as well as its material to 4340 steel, we wanted to run some physical stress tests on it. In stress simulations we determined the part that receives the most stress is the internal link. There are 264 of these on the facility. The determined force applied to these links was 5,000 N. Our simulations showed that this was acceptable and the stresses would fall below the material's yield point. To ensure this we ran a tensile test, pulling on 2 holes. The results show that deformation was in fact elastic. 11. Results and need for future research. Because of the risk associated with this type of product, much more testing and iterative design should be done. Radiation testing was also not possible and fell outside of the team's capabilities. Future research would also be beneficial, as the team only had a few weeks to gather data. Needless to say, we have achieved the required design based on limitations. For more detailed explanations or for calculations see the team's final design report. Thank you for watching.